DLL injection theory. When a process needs to use an API from a DLL, it calls the load library API to load it into virtual memory space. In our case, we want the remote process to load our DLL using Win32 APIs. Unfortunately, load library cannot be invoked on a remote process, so we'll have to perform a few tricks to force a process like Explorer.exe to load our DLL. The MSDN function prototype of load library reveals that the function only requires one parameter, the name of the DLL to load. Our approach will be to try to trick the remote process into executing load library with the correct argument. When calling create remote thread, the fourth argument is the start address of the function run in the new thread, and the fifth argument is the memory address of a buffer containing arguments for that function. The idea is to resolve the address of load library inside the remote process and invoke it while supplying the name of the DLL we want to load. If the address of load library is given as the fourth argument to create remote thread, it will be invoked when we call create remote thread. In order to supply the name of the DLL to load library, we must allocate a buffer inside the remote process and copy the name and path of the DLL into it. The address of this buffer can then be given as the fifth argument to create remote thread, after which it will be used with load library. However, there are several restrictions we must consider. First, the DLL must be written in C or C++ and must be unmanaged. The managed C#-based DLL we've been working with so far will not work because we cannot load a managed DLL into an unmanaged process. Secondly, DLLs normally contain APIs that are called after the DLL is loaded. In order to call these APIs, an application would first have to resolve their names to memory addresses through the use of getProcAddress. Since getProcAddress cannot resolve an API in a remote process, we must craft our malicious DLL in a non-standard way. Let's take a moment to discuss this approach. As part of its functionality, load library calls the DLL main function inside the DLL, which initializes variables and signals that the DLL is ready to use. Typically, DLL main performs different actions based on the reason code argument that indicates why the DLL entry point function is being called. We can see this in this unmanaged DLL main code. As stated in the MSDN documentation, the DLL process attach reason code is passed to DLL main when the DLL is being loaded into the virtual memory address space as a result of a call to load library. This means that instead of defining our shellcode as a standard API exported by our malicious DLL, we could put our shellcode within the DLL process attach switch case, where it will be executed when load library calls DLL main. To use this technique, we either have to write and compile a custom unmanaged DLL in C or C++ that will execute shellcode when the DLL main function is called, or use a framework to generate one. Since C and C++ programming is outside the scope of this module, in the next section, we'll use a framework to generate a Meterpreter DLL with MSF Venom, leveraging this technique.